Okay, so now we've talked about the kinematics, analogs for rotation. Now we're going to talk about what causes rotation. So when we're talking about motion, the thing that causes motion to happen, the thing that causes motion to change is force. And so the thing that causes rotation to happen or causes rotation to change, we call it a torque. Okay, spelled T-O-R-Q-U-E. And just when you twist or turn something, you cause a torque. So think about turning on your faucet in your house, or if you're driving, you're turning your steering wheel. All those situations are you're exerting a torque, causing something to rotate. And then here's just kind of some tools where you see that happening. Situations where torque occurs. And so the way that we calculate the amount of torque is by multiplying the distance the force is away by the amount of the force, okay? And we're also factoring in the angle of the force too, because as we'll see later, that angle matters, okay? You can also calculate torque by multiplying the perpendicular radius times the force, okay? Or the perpendicular force times the radius, okay? So there's three factors for torque. The first one is how strong the force is that's being applied. The second is what direction it's being applied. And the third is where. So this is really important because if you think about if you maybe played baseball when you're younger, or softball, I guess, you would have held the baseball bat closer to the top because you weren't as strong, and so you wouldn't have to use as much torque to cause it to swing. And then we'll talk about some other examples in a minute. But so if we look at this wrench, you have two different forces on it. The greater force is going to cause a greater torque. Okay, and here you have forces acting at different angles. You have a small angle, kind of a medium, and then a right angle here. Which one do you think would cause the greatest torque? Well, it's the perpendicular one. If you probably can think about situations where you've had to turn something, and you definitely are. It's easier to turn when you exert the force at a right angle. Okay, and that's when actually the torque is maximized. And finally, the location. So the further you are from the point of rotation, the easier it is to turn something because you actually create a larger amount of torque by increasing this radius. Okay, so the further you are away, the greater the torque. And when I was younger, I had a truck, and actually the engine would freeze up. There was a bolt like this on the front, and I would take a wrench and I would attach it to try to get it to turn over. And with the wrench itself, I wasn't strong enough to do that, but I would put a pipe on the end of the wrench to increase the radius so that if I pushed down at the very end, I had several times as much torque as I would just by pushing on the wrench, and then I was able to cause it to turn. Okay, so here we have a situation where we have this beam, and we have 1, 2, 3, 4, 5 different options for the amount of force causing it to rotate about this point right here. Okay, I want you to think about which of these forces are causing the most torque and which one are causing the least torque. So which forces cause the most torque here? And if you chose this one right here and this one right here, you'd be correct because they both are perpendicular to it. Okay, and which one caused the least torque? Would be this one right here and this one right here, because their perpendicular radius in both cases is equal to 0. So this one right there and that one right there don't do anything to rotate it, they just kind of pull on it. Okay, the next thing I want to look at, so there is same convention for rotation. If you have a counterclockwise torque, that's positive. If you have a clockwise torque, we consider that negative. The same rules apply for the vectors, so a positive torque is pointing towards you out of the page, whereas a negative torque points into the page. Okay. Okay, so here's an example, someone who is turning a wrench, and there's two ways of approaching this, and so we're going to look at it both ways. As we do, remember that torque, sorry, it's like the symbol tau, so it's like a curvy T, okay, is equal to the perpendicular radius times the force, okay, or RF sine theta, okay? So we're going to look at it kind of both ways, all right? The first one we're going to do will be to find the, let's do this one right here. We'll do this way first. So the radius here is 12 centimeters or 0.12 meters. The force is 80 newtons. And the reason we use sine of theta is because we're finding the component of the force that's actually perpendicular to the radius. So let's actually go back and do this and look at the component. So we have a component of the force that's pulling back on the wrench, okay, and that would be 80 times cosine of 60. Then we have the component that's pulling up, and that would be 80 times sine of 60. Okay, well that's why we use sine here. So it would be 12.12 meters times 80 newtons times sine of 60. Okay, punch that into our calculators, and you should get about 8.31 newtons times meters. Okay, we can also, so that would be our torque, and the units are newtons times meters. And one thing I want to point out is that these newtons and these meters are actually perpendicular. The reason that's significant is because we have, as well as that this is a vector quantity, we have a scalar quantity of energy that also is newton meters, okay, but these are scalars, and that is joules, okay. In the context of energy, a newton meter is a joule. In the context of torque, a newton times a meter, because these are perpendicular, is not a joule, okay. This is just our unit for torque. Remember that with energy and work, the force and the displacement were parallel. In this case where we discussed torque, they're perpendicular. Okay, so let's try it this other way. We want to find out the length of the radius that's perpendicular to the force. Okay, and the way we do that is by actually taking the force and tracing it back, okay, as far as we need to find when the radius is perpendicular. So I took the liberty of using like a kind of a straight line to draw these. So if you trace the force back, you're looking to the point where it comes closest to this point of rotation, this axis of rotation, and if you trace the line from the axis to the closest point, you get a right angle. And so this is the place for which the radius is perpendicular, okay, which if this is 0.12 meters right here, okay, and let's see, this would be, I'm trying to figure out my angles here, so this would be, I believe, 30 degrees. Yes, because these are alternate interior angles, so that's 60, so that's 30. So this right here would be 0.12 times cos of 30, or 0.12 times sine of 60. Okay, so we get the same thing. Torque equal to perpendicular radius would be 0.12 sine of 60 times 80 newtons, okay, and the same three things we multiplied here will end up with 8.31 newtons times meters again. And there you go, that's torque.